I'm going to start with the summary of section 1.5 first. Look at the first point you're going to have. When a constant is divided, I'm talking about limits now, okay? So when a constant is divided by something that approaches 0, the ratio approaches infinity or negative infinity. You just got to mess with the signs. So for instance, let's look at our calculator here. Let's start with a constant. 1's a constant. And then let's divide it by things that are approaching 0. So let's first divide it by 10. All right, that's not a very big number. Then let's take that 1 and let's divide it by 1. Then let's take that 1 and let's divide it by 0.1. 1 divided by 0.01. 1 divided by 0.001. So you see what's going on? When we're talking about a limit now, if the limit of your numerator is a constant, which we can figure out quite often by substitution to find the limit of the numerator, and then the limit of the denominator is approaching 0. The ratio of that constant divided by something approaching 0 just flat out keeps getting larger, doesn't it? So it's going to infinity. So how would we make it go to negative infinity? Divided by something approaching 0 from the left. Or have a negative constant divided by something on the positive. See what I'm saying? As long as the signs are different, you'll get the negative infinity. So does that first summary make sense? The first point of the summary? Now the second point of it. Again, limit. When a constant is divided by something that's approaching infinity or negative infinity, the ratio approaches 0. Okay, so it's kind of the opposite idea. So we can find the limit of the numerator by doing whatever we do, probably substitution. Turns out it's a constant. And then the denominator is approaching infinity or negative infinity. And this time the sign actually doesn't matter. So let's take our constant. Let's divide it by 1. Ooh. So let's take 1, divide it by 1, we get 1. All right, now let's take 1 and divide it by 10. 1 divided by 100. 1 divided by 1,000. And what is happening to our ratio? It's getting smaller. It's approaching 0. So, do these two summary points make sense? All right. Then let's go back to here. So turn to page 83. A limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. So far we've said that it does not exist, and then we've hinted around about how, but if it's going up forever, we could call that infinity. If it's going down forever, we could call that negative infinity. But we've just kind of hinted around at that. But now they're saying it, okay? If the function increases without bound, which means forever, then the limit as x approaches c is infinity. If the function decreases without bound as x approaches c, then the limit is negative infinity. And this leads us to our definition of vertical asymptote. If f of x approaches infinity or negative infinity, as x approaches c from the right or from the left, then the line x equals c is a vertical asymptote of the graph of f. Now, we talked about continuous functions. That function is discontinuous at the asymptote, isn't it? It's got to be, okay? And in fact, it's a non-removable discontinuity at the asymptote. So, if the graph of a function f has a vertical asymptote at x equals c, then f is not continuous at c. So whenever the limit equals infinity or negative infinity, and it's a vertical asymptote, then the function is not continuous there. Okay? Now, if you can tell that you're going to have a vertical, well, how do you tell that you're going to have a vertical asymptote? It says if f of x approaches infinity or negative infinity as x approaches c. So we would need to find the limit of f of x as x approaches, in this case, 1 from the left, and then the limit as x approaches 1 from the right. Now, why are we doing it from each side individually? Well, because look how the limit works out. Okay? And I don't want you to see that yet. Because it makes a difference, doesn't it? But I can't find the limit of f of x as x approaches 1, and you'll see why in a minute. But look, if x approaches 1 from the left, and this is an idea y'all said a while ago when we were talking about that summary. If x is approaching 1 from the left, that's from numbers that are less than 1. Well, a number less than 1 minus 1 is negative. So the denominator is going to 0, but it's going to 0 through the negative numbers, isn't it? The denominator is always going to be negative as x approaches 1 from the left. So a positive constant divided by a denominator that's approaching 0, we get infinity. But it's, well, we get infinity or negative infinity. In this case, it's negative infinity because a positive divided by a negative is negative. I mean, your middle school teacher that taught you that wasn't lying. That's the truth. It's always the truth. A positive divided by a negative is always negative. So it's negative infinity. Whereas when we do this limit over here, as x approaches 1 from the right, that's numbers bigger than 1. Well, a number bigger than 1 minus 1 is positive. So a positive 1 divided by a positive, we're going to get a positive result. So that's why we get infinity in this case. Now do you see why I can't find that limit? Because the limit from the left does not equal the limit from the right. So that limit does not exist. So look what happens. We get negative infinity as one of our one-sided limits, positive infinity as the other one-sided limit, which means the limit does not exist. With me? All right. So what have we learned so far? What we've learned so far is whenever you have a vertical asymptote, it occurs because the limit as x approaches c is either infinity or negative infinity, and as we've seen here in this example, maybe even one of each. It's possible to have this, right, where the limit from the left of 1 is infinity, the limit from the right of 1 is also infinity, and so we would say the limit equals infinity, but it's still a vertical asymptote, isn't it? Okay, they did that. We could have this situation again where it goes to infinity from one side, negative infinity from the other, or we could have negative infinity from both sides. So any of these things can happen. And how do you know which one is happening? By finding the limit as x approaches c from the left, find the limit as x approaches c from the right, and see what you get. Okay? Questions? All right. This theorem's helpful too. Let f and g be continuous on an open interval containing c. If f of c does not equal 0 and g of c does equal 0, and there exists an open interval containing c such that g of x does not equal 0 for all x not equal to c in the interval, who's confused? If your hand's not in the air, it's because either you're not paying attention or you're lying. Then the graph of the function given by h of x, which equals f of x divided by g of x has a vertical asymptote at x equals c. Yeah, we need a paraphrase of this, don't we? So here's my paraphrase. Vertical asymptotes means that after dividing out common factors, that is, removing removable discontinuities, vertical asymptotes occur at x's that make the denominator equal 0. So, this theorem means, and you need to write that down, one of the reasons that we worried about removable and non-removable discontinuities in the previous section is for this, okay? If you remove all of the removable discontinuities and you still have an x-coordinate or 2 x-coordinates or 17 x-coordinates that make the denominator equal 0, then each of those x-coordinates that makes the denominator equal 0 will be a vertical asymptote. Notice this theorem doesn't tell you whether or not you have a vertical asymptote where both sides go to infinity or both sides go to negative infinity or one of each. It doesn't tell you that. But it tells you that if you have removed all the removable discontinuities and you still have places where the denominator equals 0, those places are vertical asymptotes. Okay? With me? All right. Let's look at page 85. Example 2. It says determine all vertical asymptotes of the graph of each function. So let's just go through these fairly quickly. We'll do the math. Well, you'll do a lot of the math later. Let's just look at the idea here, okay? So on A, there's no way, there's no common factors to divide out. There aren't any removable discontinuities for that function, okay? And when x equals -1, the denominator is 0. So the theorem says that we can conclude that x equals -1 is a vertical asymptote. And if you graph it, let's see, that would be this one, you see that that's what you get. Okay? Then let's look at B. On B, we try to factor. So we're doing everything we can so that we can remove any removable discontinuities. But nothing divides out. So we factor the denominator, the numerator's not factorable, nothing divides out. So in this case, we will get 2 vertical asymptotes. Because when x equals -1, that makes that parentheses equals 0, makes the denominator equal 0, vertical asymptote. When x equals +1, that makes the other parentheses equal 0, which makes the denominator equal 0, another vertical asymptote. Again, the theorem doesn't tell us where the graph's going to infinity, where it's going to negative infinity, but it does tell us we have vertical asymptotes there. All right? And then C. Well, if you rewrite the cotangent of x as cosine over sine, all right, that's going to be periodically, you're going to have a denominator of 0, aren't you? So you're going to have a bunch of vertical asymptotes. Normally, any book will restrict the domain so that you don't have an infinite number of vertical asymptotes. That gets a little tough to graph, infinity and all. But they'll usually, restrict it to 0 to 2 pi or -pi to pi or whatever they restrict it to so that you don't just have an infinite number of them. All right? All those make sense? All right, let's look at example 3 on page 86 now. Determine all vertical asymptotes of the graph of, all right, and we're not worried about every little step right now. I want you to see the big picture. Here's what we do. To find all the vertical asymptotes, we take our original function and we factor everything we can factor. We factor the numerator, we factor the denominator. Turns out there's a pair of common factors that we can divide out. Now, you divide out factors, not terms. Okay? So, all the removable discontinuity gets removed. All right? And we're left with this. Well, doesn't that mean that x equals -2 has to be a vertical asymptote? There was a discontinuity at 2, but we removed it. So that was just a hole. We removed it. Okay? But here we have this non-removable discontinuity where the denominator equals 0, so x equals -2 is a vertical asymptote. Okay? And that's what our theorem tells us. Now, to actually know what the graph looks like, we would need to find the limit as x approaches -2 from the left, find the limit as x approaches -2 from the right. So we see that as x approaches -2 from the left, the limit's -infinity. So I know the graph goes down as it approaches that vertical asymptote from the left. Then the limit from the right is +infinity. So as the graph approaches the vertical asymptote from the right, it goes up. Don't forget the little hole because it was discontinuous at 2 to start with. And now, we haven't really learned enough to know what the graph does when it gets farther away from that vertical asymptote. We will, but right now I'm not worried about that. I'm just worried about you getting it correct near the vertical asymptote. Okay? Any questions on that example? All right, example 4 on page 86 again. Find each limit. Now, it's the same function. We're finding the limit as x approaches 1 from the left, and we're finding the limit as x approaches 1 from the right. And I have a way that I think works a little better than what they've got here. I get a little confused trying to, all of a sudden they're getting a graphing utility out. No, we need to be able to do these without a calculator. With a calculator, sure. But I mean, how hard is it to find a limit when you can graph it on your calculator? You can do that, right? So we need to be able to do it without a calculator as well. So over the years, I've devised this technique. A true mathematician with a PhD would probably come in here and knock me off my stool because I'm sure there's some incorrect technicalities in this that aren't just right, but you're going to understand this, okay? Here's what I do. Let's ignore this one. Let's find the limit as x approaches 1 from the left of this function. Factor everything. All I can do for this particular problem is take out a greatest common factor of x from the numerator. All right? And now I'm combining a bunch of different limit theorems. Okay? One thing we can do is we can take the limit of the numerator and the limit of the denominator, right? Once I take the limit of the numerator, I can find the limit of that by substitution, can't I? Now, I'm not concerned with the numbers, but I can substitute a 1 in there. I won't get 0. I am concerned with that. I will not get 0 when I replace that and that with a 1, will I? So I won't get 0. So think back to our summary that we started with, okay? A constant divided by something approaching 0, we're going to get infinity or negative infinity. We're going to, isn't that what's happening? We're going to get a constant up here, right? And we're going to divide it by something that's approaching 0. How do I know it's approaching 0? Well, because if I stuck a 1 in there, I would get 0. So as I'm getting closer to 1, the denominator is getting closer to 0. So the denominator is approaching 0. So our task is to figure out, is the limit going to be infinity or negative infinity? Our task is to figure out the sign. It's just to figure out the sign. Okay? So if I did find the limit of the numerator by substitution, that first factor would be positive, right, because we're approaching 1. Even if it's from the left, 1 is a positive number, so that one's positive. And then the second parenthesis, as x approaches 1 from the left, a number smaller than 1 minus 3 is negative, isn't it? So I've got a positive times a negative, so the result of that's negative, isn't it? Now let's decide the sign of the denominator. It's approaching 0, that we know, but is it going to be approaching 0 and be positive, or is it going to be approaching 0 and be negative? Well, if it's approaching 1 from the left, that's from numbers smaller than 1. A number smaller than 1 minus 1 is negative. So all of this is to figure out I've got a negative divided by a negative, which is, so that's why the limit is positive infinity. Now, you're going to do enough of these that you'll factor it and you'll figure out the appropriate sign in about 5 seconds. It won't take you all that long to do. But do you see what I did, and do you see why I did it? Let's do the same thing on that second limit. It's just the limit from the right. Okay? So we've got the same function. We factor it, and we're faced with the exact same thing, aren't we? We see that the denominator is approaching 0. We see that the numerator is going to be a constant that's not 0. It needs to not be 0. Because if it is, nobody knows what 0 divided by 0 is. Okay, so that's no good. So it needs to be a constant other than 0, which it will be. So decide the sign. If I substitute in a 1 in the numerator, the first factor of x will be positive because 1's positive. If I substitute a 1 into the second factor, even if it's approaching 1 from the right, that's like 1.1. Well, 1.1 minus 3 is still negative, isn't it? So that second factor will be negative. And let's decide, so our numerator is going to be negative. Let's decide what our denominator is going to be. As x approaches 1 from the right, that's from numbers larger than 1. So I'd be like 1.1. Well, 1.1 minus 1 is a positive number. 1.01 minus 1 is a positive number. 1.00001 minus 1 is a positive number. So the denominator is approaching 0, and it's positive. So I know that it's infinity or negative infinity. I've got a negative numerator divided by a positive denominator. I get negative infinity. Now, I kind of wrote this wrong. It's not really thus x equals 1 is a vertical asymptote. I already knew that. As soon as I factored everything and knew that I could not remove that x minus 1 as a factor, I knew at that point x equals 1 is a vertical asymptote. It should be thus, I know what the graph looks like now. Okay? You with me? Think you'll be able to pull that off? Yeah, I think so. All right. Properties of infinite limits. Basically, remember this. The only thing a constant can do to infinity is possibly affect its sign. If you add or subtract a number from infinity, it's still infinity. If you add or subtract a number from negative infinity, it's still negative infinity. No matter how large a constant you come up with, infinity is so much larger than that constant that it completely dwarfs it. The constant is meaningless. Okay? However, when you're multiplying and dividing, it can affect your sign. Positive times positive is positive. Negative times positive is negative. Positive times negative is negative. Negative times negative is positive. Okay? Now, one thing we mentioned in the summary I haven't talked about yet is this. I haven't talked about yet since the summary. constant divided by a denominator that's approaching infinity or negative infinity is always 0. And we don't have to say 0 from the left or 0 from the right. It's 0. The limit is 0. Okay? Questions on that? Ooh, we're back to where we started. Hooray! Let's do some examples. What do you say? Let's start with number 4. Page 88. Determine whether f of x approaches infinity or negative infinity as x approaches negative 2 from the left and from the right. So don't let the rest of the graph distract you. As x approaches negative 2 from the left and from the right. So that's the vertical asymptote they're asking us about. Ignore the others. So look at the graph. Do this by looking at the graph. You don't have to figure it out yourself. You don't have to know that f of x equals the secant of pi x over 4. You don't have to. As x approaches negative 2 from the left, where's the graph going? To infinity or negative infinity? Negative. And as x approaches negative 2 from the right, where's the graph going? Positive infinity. There you go. All right, so we still do limits graphically sometimes. We also find limits using a table. Number 7. We're supposed to determine whether f of x approaches infinity or negative infinity as x approaches negative 3 from the left and from the right by completing the table. Use a graphing utility, blah, blah, blah. So, if we use our calculator to fill in this table, if f of x equals x squared divided by x squared minus 9, use your table function. And let's see if we get basically the same things. For negative 3 point, looks like I might have rounded these to knock one off. As x approaches, or when x equals negative 3.5, do you get something like 3.769? Do you get exactly that, or do you have more digits? 3.769. Okay, I thought I might have chopped one off. And then see what you get for negative 3.1. And negative 3.01. And negative 3.001. And where does it appear to you our graph is heading as x approaches negative 3 from the left? Looks like infinity to me. I think that's getting large really quickly, isn't it? All right, and then see what happens as you approach negative 3 from the right. Negative 2.5, negative 2.9, negative 2.99, negative 2.999. Everybody get something heading towards negative infinity? All right, then write out your conclusion. Our conclusion is the limit of f of x as x approaches negative 3 from the left equals infinity. And the limit of f of x as x approaches negative 3 from the right equals negative infinity. They didn't ask us to, but can we sketch a rough graph of that? Yeah, you just do this. You put a vertical asymptote there at negative 3. As x approaches negative 3 from the left, you'd get that. From the right, you'd get that. And I don't know what it happens the further away we get from our vertical asymptote, but I know that's what it looks like near it. Okay? All right, number 26. Uh-oh, we're heading towards infinity. That was a big jump. Oh, that's only funny to me. It's amazing how often that happens. Find the vertical asymptotes, if any, of the graph of the function. So h of t equals t squared minus 2t divided by t to the fourth minus 16. Factor, 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 factor. Can we factor the top?
No.
Factor out of t. Can we factor the bottom? It's a difference of two squares. So it'll be the square root of t to the fourth, which would be t squared, plus, and then minus in the other one, 4, because that's the square root of 16. That's right. We're not through factoring. Hey, if things divided out here, and we didn't need to keep factoring, then go ahead, divide them out. But we need to keep going. All right. And once we get this far, no. A sum of two squares is not factorable. What do we divide out? Our t minus 2's. Now, are there any t coordinates that will still make this denominator equal 0? Negative 2. Anything besides negative 2?
No.
No. This first parentheses can never equal 0 because we're just dealing with real numbers. All right? And if you tried it, if you did that, equals 0, t squared equals negative 4, t equals a square root of negative 4. No, it doesn't, because we're just working with real numbers. Okay? So that means t equals negative 2. Oh, sorry, I forgot to show you that after I divide them out. So that means that t equals negative 2 is a vertical asymptote. And they don't ask us, but what happened at t equals 2? We removed it. It was removable. So what was there in the graph instead of an asymptote? There was a hole. So they don't ask you that. You don't have to put that. But you need to realize that's what was going on. There was a hole in the graph there. If it's because it makes the denominator equal 0. Okay? All right, and this is a good time for me to talk about attempted murder. Because some of you are going to try it. You're going to try to kill me. You are. I consider this attempted murder.
That was just silly. That was silly.
Oh, one of you is going to do it on the quiz, on the test. Maybe 7 or 8 of you. Because that's nonsense, right? So, you're trying to give me a heart attack when you do that. Because I don't know how it works. I just see people do it. And I know what you're doing. You're thinking to yourself, I know I'm supposed to be able to do something with this. So, instead of sitting here and leaving it blank, I'm just going to start marking a few things out. But that doesn't work. It doesn't. Don't do it. I would rather you make a guess some way than that. Because I'll have you arrested. That's attempted murder. And it's premeditated. Well, I don't know. It may just be panic. You might have a self-defense argument. I don't know. I hadn't thought of that. All right, let's take a look at 35. Find the limit. We've got to find the limit x squared over x squared minus 9 as x approaches 3 from the right. All right, 3 from the right. If it's factorable, factor it. So we do. And now, we need to do some thinking. Okay? What's the limit of the numerator? What's the limit of x squared as x approaches 3 from the right? 9. It's a constant, isn't it? It's a positive constant. You can actually write the 9 if you want to, or you can just do positive. Which way? Okay? Now, finding the limit of the denominator. If I substituted a 3 in there, what do I get? I get 0. So substitution doesn't actually work. Substitution in quotes doesn't actually work here. So now's when we reason it out. We've got a constant divided by something approaching 0. We're going to get infinity or negative infinity. We just got to figure out which one. This first parentheses here, positive or negative? It's a 6. You can either write down 6 or you can write down positive, or you don't have to use my technique. You can look what the book did and use theirs. But then that second one is approaching 0, but I do need to know whether it's a negative factor or a positive factor, don't I? All right, since it's approaching 3 from the right, that number's larger than 3. So a number larger than 3 minus 3 is a positive number. So it's approaching 0, but it's a positive number. So if everything on there is positive, so I'd be a positive divided by something approaching 0, but is positive. So positive divided by is means it's infinity, not negative infinity. So you've got to get comfortable with this idea that a constant divided by something that is approaching 0 is either infinity or negative infinity. And you've got to recognize that. If not at this step, you've got to recognize it there, that that's what's going on. That when you find that limit, it's going to be a constant divided by something approaching 0. And then it's simply, what's the sign? With me? All right. There we go. Page 88, 1 through 51 odd.